before Andy's introduction, I should mention that the schedule is a little fishy. There is no talk by Steve Olody or by Larry Paulson this week.
Yeah.
So,
Yeah,
ignore those.
something had gone wrong, right?
Yeah.
We'll blame the against you.
Right, so should we start?
You're ready.
Right, pleasure to introduce Bas Spitters. So I see that he's got two major buzz things in the title, not only homotopy type theory, but probabilistic programming as well. My God, take it away.
Thank you. But there's even one more buzzword, so that's synthetic topology.
In some quarters, that would be a real term.
But the question is really quite simple. So there's a library for probabilistic computation in the Coq system, and we try to, and this is the basis for Certicrypt, which is a system for certifying probabilistic computation. So certifying cryptography protocols there. And the way it does this is you take discrete measure theory in Coq, and then you follow the monadic approach to probability theory. So this has been, this came from Giry, and then later this was popularized in programming by Jones and Plotkin. And so there's a nice presentation of this for people familiar with programming, which like the CPS translation. So a measure would be a map from an underlying set to 0, 1, and then so those would be the measurable functions between 0 and 1, and then you map to 0, 1 itself. So you give a measure to that. And of course you need to refine this because these things need to be monotone, need to be summable, and they need to be linear. And you can write this all down in Coq, and it works. There are a number of problems with it. One is that Coq cannot actually prove that this is a monad because you would actually need to have functional extensionality. So the way to do this is you enfold.
Can't you just postulate function extension?
Yeah, so that's where we're getting to. What they do is actually formulate the monad laws and then do them pointwise, and then you can scale those things. The first question is, so here's an example of what a coin flip looks like in this framework. So a coin flip, you take just the booleans, and then for every function from the booleans to 0, 1, you take a half time the value of f at true and a half time the value of f at false. So the first question is, when you connect it to this functional extensionality, and connect it to a lot of, so if you look at this library, they have an awful lot of setoids in there, and as they should have, but then the question is, can we actually avoid this? And this is what some people call the setoid hell. Because it gives you quite a lot of extra infrastructure, just a lot of extra bureaucracy, so you want to avoid that. And the second one is, can we extend this to 0, 1 and general continuous spaces? And there's actually a clear motivation for this. So one is from machine learning, and I'll say more about this later on, from Augur version 2. So this is, we're actually collaborating with these people now. But I'll have a slide of this at the end. But for machine learning, you actually need to have not just discrete measure theory, but actually measure theory over continuous spaces. The other one is for differential privacy. And again, I had a student working on this extension of the Easycrypt system. So the Easycrypt system is an involvement of the evolved from the Certicryptsystem, and it's actually built on this. And I've been using this to with collaborators to verify secure multi-party computation. And then I recently had a student that finished the formalization of some differential privacy in this system. And again, what you need here is an extension of the system from these discrete measures to actually also have continuous measures. So there's a very clear motivation for this. Of course, once I've done this, I'm just going to do all kinds of fancy stuff and buzzwords and so on. Okay, but let's go back to the setoids. And this is, everyone here knows this. homotopy type theory is a clear way of adding quotient types and functional extensionality to type theory. So this is a very clear motivation. So instead of using setoids, we can just use quotients by using univalent homotopy type theory. And we look at univalent homotopy type theory as an internal version of a type theory with, an internal type theory for a generalization of setoids, so groupoids, high groupoids, and so on. So this is a way of actually getting rid of the use of setoids just by adding axioms. This hot library, the one we're using for the Coq formalization, is the one we've built with a number of people that are also here. And we have a paper at CPP about this. So I was in Paris and there was a very nice talk by Gordon Plotkin about, so what do we actually want from a semantics of, this is just a picture, so sorry for the resolution. So what do we actually want for a framework for probabilistic programming? And so he's very clear, he wants continuous and discrete data types, and a rich variety of functions between them, random choice, again, discrete and continuous distributions, conditioning, I won't say much about this, and a rich type system, so some product function types, probability types, recursive definitions. What I'm going to present later on is the semantics that carries most of these features. I haven't looked too carefully about whether we have everything, especially if we didn't look at conditioning. But we're actually going to connect up also to an actual programming language that does all this. So first question is, how do we actually formalize probability theory? And so the classical probability theory, you start from sigma algebra and you look at the measures of those sigma algebras. So sigma algebra is just a collection of sets closed under countable union joints, and then a measure is a sigma additive map to real numbers. What turns out to be better behaved in semantics is the notion of, I'm running ahead of myself, then the observation by Giry. There are several subcategories of topological spaces or domains on which you can look at this construction. So you take space X and you look at all the measures on X. And this will again have a topology on it. And for instance, you can do this on, say, the Polish spaces or on measurable spaces. There are a number of choices. There are also collections of domains on which you can do this. And actually, if you're looking at domains, it's nicer not to use measures, but to restrict the measure just to the open sets. And the open sets actually carry all the information. So if you're on a compact regular space, compact Hausdorff space, then you can reconstruct the measure from just the valuation, from its value on the open sets. So what we're going to do is, following the what is common in domain theory, just restrict to the valuations and forget about what happens in closed sets. So now we need to formalize topologies in. Yes.
So to reconstruct the measure, it's essentially character reverse extension theorem or similar.
Yeah. So now we need to formalize topological spaces in Coq. We need to build up a whole infrastructure of type classes to carry around proofs that functions are continuous and so on. We could do all that, but I mean, I had this other first word in my title, so we're going to take a different route. And this is the one we're going to take. So there's the idea of synthetic topology, which is also very much in the flavor of what we're doing with synthetic algebraic topology, for instance, in HOT. And this probably comes from Dana Scott, who observed that wouldn't it be nice if domains were actually sets? And that doesn't work classically, but if you go to constructive logic, this can actually be made to work. And people like Martin Hyland and Pino Rusli have done a lot of work in this direction. So you add some axioms to just the axioms of topos theory, and then you can get your can capture your domains inside this topos. So and all the maps will actually be continuous. So this is a very nice way of working. This has been copied to not only domain theory but also topology, and you could argue that Brouwer was the first to do this. So he would have objects in his mathematics, and they would all have topological structures, and all the maps are actually continuous. But more recently, people like Martin Escardo, Paul Taylor, Steve Vickers, Andre Bauer, they have worked a lot on synthetic topology in various similar ways. So the idea is that every object will carry a topology, and all the maps between them will be continuous. And so one main idea is that you start from Sierpinski space, because this classifies the open. So instead of having a separate collection of, instead of having every set carry a topology, you classify the topology by looking at maps into Sierpinski space. So Sierpinski space is just the space with 2 points and one open around one of the points. And then you can see that the opens of X are precisely the maps are precisely correspond one-to-one with maps from this one to Sierpinski space, because you look at the inverse image of this map. So you can have the characteristic map, such an open set. And then people are working on convenient categories or type theories of topological spaces. So that's very much this style. And then finally, there's synthetic computability, and you can, there are at least two ways of capturing computability. One is just Turing machines, but you can also look at type 2 Turing machines, where you actually have continuous data types. And then this, you would again have such a structure that looks very much like Sierpinski space, but then the classifier for semi-decidable subsets. And you can build an awful lot of, just by working constructively and working with this classifier, you can build up a lot of computability theory just inside. And the nice thing is, and of course this again connects to what's happening in domain theory, because that's also a way of capturing computation. There's a common generalization of these three approaches that works by capturing some abstract properties of sigma, and this is the dominance axiom that says that maps classified, one way of stating it briefly is that maps classified by sigma actually compose. So you would, so typically this classifies a collection of monos, and then if you have two of those monos, they actually compose. The nice thing is that this actually recently showed up in the work by Andy and Ian in cubical type theory, where it also was very nice to capture the cofibration. So this is actually connected also to the cubical type theory.
How do you implement this Sierpinski space in type theory?
That's a very good question. That's 2-3 side stuff. So
okay.
I'll come back to it. Yes. So, and we need a few more actions. So the yeah, I'll say more about this in a minute. So what we we're going to add a new type that's actually the Sierpinski space. So let's consider the one-point compactification of the natural numbers. So those could be seen as the type of increasing binary sequences, and so you look at the first point where it actually jumps, and that's the connection to the natural numbers. And then you would also have a point at infinity. And one of the axioms we want is weakly sequentially open, and that says that the topology you get on the one-point compactification actually coincides with the metric topology here. And this can also be expressed, so this is the intuitive reading of that. This can also be expressed as if you have a function from the one compactification to sigma, and if it happens to be 1 at infinity, then the existing natural number was already 1. So there's no isolated, so the topology on the one compactification is not discrete. So this obviously contradicts classical logic, but it holds in our models. The models will come back in, will come in a couple of slides. And there's a stronger theorem that says that this one is actually metrizable in compact. And this will be this is key good good measure theory on continuous spaces. And this is just compactness of Cantor space. So there was a student of Andre Bauer, and he developed quite a lot of analysis at this level of generality. And the interesting observation there is that countable choice is often not needed. So often in constructive mathematics, you would take countable choice for granted, but in fact it's not necessary. And one of the interesting things about homotopy type theory is precisely that countable choice is not provable, as Giry showed a couple of days before. And so it's natural to try to develop as much as possible the analysis without using countable choice. So that's also something we contribute a little bit to. Yeah, so how do we get these models? I mean, one thing is just adding axioms to our type theory, but we better have a model in mind before we do this. Well, as you all know, the internal logic of the internal language or the internal logic of a topos will just be intuitionistic higher order logic or some dependent predicate logic. And then we have the standard axioms for continuous computations. Those go back to Brouwer, to Kleene-Vesleyrealizability. So this is the Kleene's second algebra. I'm not going to be precise about what that is, but this has been rediscovered in the Weyrauch school to computability theory. This is what who call it type 2 theory of additivity. And the interesting thing is this has been recently implemented in Newville in a very computer science way with names and handlers. So this, I think, is very interesting that this is now also available in proof of systems. And this realizability, of course, gives us the realizability topos. So we can actually model the continuous computations very nicely using the axioms of a topos. And then there's another class of models. This is we go back here. So this was about synthetic computability, realizability. The other one is about synthetic topology, and they're actually connected, those two. So those are the so-called big toposes or gross toposes. So they're sheaf toposes over some subcategory of topological spaces. So typically you take, say, T0 countably based topological spaces with certain covering on them, and then you take the sheaves over those. The interesting thing is that, so those are two models for the axioms we're looking at, for the axioms of constructibility, intuitionistic axioms, if you like. And there's a paper by Steve Audi and Andre Bauer that showed that you can actually embed the realizability topos inside these big topos. So that's actually very nice. And both would be settings where we actually have our models satisfied. So now we actually made the problem worse, because before we were only going to formalize topology in type theory, and now we even need to formalize topos theory in type theory, so that's even worse. Fortunately, there's a very strong research connection, research direction, and that's also what you heard Egbert Rijker talk about before, for instance, and Thierry Coquin, about having homotopy type theory as an internal language or the internal language for toposes. So this fits that general scheme. So we use homotopy type theory as the language for higher toposes. And what we've shown before in a paper with Egbert is that if you look at the H sets in homotopy type theory, they actually form a predicative topos. And this means that your power sets are actually not small, but they're actually large. So they live in the following universe. And this predicativity is something that will come up in the talk. Yeah, so Mike Schulman has at least put this in writing, but you can also find it in the homotopy type theory book, for instance. That both we can generalize both the Grothendieck toposes and the realizability from the one topos case to the higher topos case. And there are a number of results. So maybe most importantly, the simplicial sheaves by Szynski and Schulman. They worked out that they actually follow the axioms of homotopy type theory, but with weak universes. You've heard Giry speak about cubical stacks, and that quite a lot has been done, but it's not entirely clear whether we can do all quotient topologies. There's work on cubical assemblies by people from CMU that does the realizability. There's also the cubical model that has been formalized in Newport, and there have been ideas of extending this to actually get a model of homotopy type theory where we also have this computability, this real computability built in. So there's quite a bit of evidence that this can be made to work. All of these approaches have some small issues, and we can hope that they can be solved. So for now, we're going to just accept that this can be done, and we're going to actually give more motivation to work on this by showing that this is actually useful. So this is our second use of HOT. So the first use of homotopy type theory was to avoid the functional extensionality quotients on the set of it. And the second one is to do predictive constructive mathematics without choice to apply to probabilistic computation. So this is, Andreas, this is your question. There's a long-standing, I'm going to define sigma here. So what we're using is the Cauchy reals in homotopy type theory, and those are described as a higher inductive type in the homotopy type theory book. This is one of the most complex constructions in homotopy type theory, and this needs to be done as a higher inductive type because we don't have countable choice, and therefore we do this in one go. And this has been formalized by an intern, by Gaëtan Gilbert, who did an internship with me. We're also using the hot classes library. That's a port of the math classes library, but to hot. And this is the library we developed to have an abstract approach to do efficient, but also verified numerical computations inside Coq. And because we're doing inductive types, we need an extension of Coq with induction, or actually induction recursion in this case, and there's now a branch of Coq that actually does this. So we're actually building on this. So there's quite a lot that actually goes into this, but that also makes it exciting. So it pushes several research directions. Now the question that arose from the Cauchy reals, so how to do the Cauchy reals in Coq, that also motivated the definition of the flat domain in type theory. And this has been a long time story because we want to know how to do partial computation. So the one motivation is to have partiality. So the language of type theory only gives you total computation. So how to do partial computations in type theory. So we want to define the flat domain on, say, an H set. And the question is, how do we do this? There have been co-inductive definitions. The problem is that if you look at the co-inductive definitions, so the co-inductive definitions either tells you, I give you now an element of A, or I'll give you something later. And then of course if you keep on postponing, then you get the bottom element, and then you want to identify, well, the thing that doesn't quite work in that setup is if you want to identify later A and later A, for instance. So the bi-simulation doesn't give you the equality, and that's something that doesn't quite work. And then there are a number of variations, so people have tried to do quotients on this, but that doesn't quite work, and that's for the same reason as you have here. So if you do the quotient, then you actually need the countable choice to actually show that you get a monad. So that doesn't quite work. So the nice observation by onthe and is that we can actually do this construction, and we look at the way this is solved for the Cauchy reals, where we use the higher inductive type, and here instead we use the free WCPO completion. And that's precisely what you want it to be, because you take a set and you want it to turn into omega CPO. So that's precisely what you do. You say you freely, higher inductive types or higher inductive types precisely give you the free construction, the free algebras. So you just write down what you want it to be. So you want it to be a set, you wanted to have a bottom element, you wanted to have an element for each element in A. We're going to make a less than relation on this new type we're defining. And then we're going to say, well, if we have a sequence of those things and the sequence of elements of a bottom and the sequence is increasing, then we can actually take the supremum of this. And then at the same time, of course, we need to say that this relation satisfies the expected relations, the expected equalities. And then if we bundle this all up in a high inductive type, then it actually works. So that's a very nice use of high inductive types because it allows us to precisely say what we want. We take a type and we wanted to make it really into a omega CPO.
So this must satisfy the expected relations. Is it a order?
Yeah, well, it's an order, and bottom is less than. Yeah.
And then that thing is the limit of the.
Yes,
yeah,
precisely. Yes,
all that sort of stuff.
Yeah, I could have added 2 more slides giving all the conditions, but I don't think anyone would be.
Just reality check here for me. I mean, we don't actually know what an HIIT is in general, but we know one if we see one. Is that roughly speaking true? I mean, I can see that makes perfect sense.
That makes perfect sense.
But I would be unable to give a general scheme of what such a thing was.
Well, even for inductive types,
Yes.
there's no completely satisfactory theory yet.
And let alone any meta theory about consistency and
Yes,
so
yes,
on.
but of course, quite a lot of work has been done, and this is a special case where this is actually a quotient inductive type. So it's all on the set level. So it's easier. And actually, sorry. So I take that back. So quite a lot has been worked out by Thorsten Alteke and students on quotient inductive types.
I can do. I mean, I have a conjecture that any quotient inductive type you can probably do.
You do it in a set overall.
Well, no, I was going to say you can do it by simultaneously defining an inductive type and a quotient. Is that? Do you think that's true? I mean,
yes,
any example I've seen is true.
Yes.
Okay.
But still, we need to go back to the question about even inductive type, where the thing's missing.
Yes.
But yeah, this one's I think well understood now.
So somehow an is somehow I feel I could probably understand that better than a hit.
Yes.
Anyway.
Well, to some extent, of course, we should ask Andreas about inductive recursion because they've been in ACTA for a long time, and you seem to be happy with using ACTA. So it's
and actually, a question really for Andreas in a sense that so you were showing us something quite cool about delay monads in cubical. Suddenly, the equality was working out nicely. Would that be true here? Do you think? I mean, if I went into cubical type theory and started making some definitions, could I get the right notion of equality for a co-inductively defined A lift?
That might actually work. Yes.
And that would be quite nice.
Yes.
Actually. Yeah.
Yes.
So is the reason using by simulation as equality doesn't work because it requires choice? Is that right?
Yes.
So, but by defining this free omega CPO completion, you do not yet get ontopy choice.
No.
No.
No, that's a nice thing. Also for the Cauchy reals, you actually have the construction, and the construction can be made in any topos, for instance.
Okay.
And it actually has been checked that you get the right construction in every topos. But
is countable choice not provable in hop? Is it inconsistent with it, or it's not? Is it?
No. I mean,
you could add it.
It holds in the simplest.
Yes. Right.
No, it's just, so it's one of the examples that Giry actually shows in his cubicle stacks. So he was building these cubicle sets precisely to show that we cannot derive it.
Don't you still have to quotient this under, I mean, equalities for the inclusion in both directions?
Yes, so that's what I said very briefly here. Yes.
And there's a set truncation.
And there's a set truncation here. Yeah, so this gives a nice structure. This actually gives you a partiality monad, so that means you can also do partial computations in type theory. And the motivation for this is the slogan is partiality as an effect. So you can do partial computations, but you will just use the IDs from effectful programming. So I think that's a very nice thing. And now we define our sigma as just partiality monad applied to 1. So we have a 1-point space and we add a bottom element. And that's precisely what Sierpinski space is.
And see, there's a typographical problem here. Yeah. You can't call it sigma.
No. and sigma is already overloaded in type theory. Yes. That's a bit of a problem. Sigma is standard in quite a few classes. What is nice is that I might say a bit more about this. So in essence, we reflect all the decidable propositions into the booleans, and now we have semi-decidable. We have a classifier for semi-decidable propositions, so we can reflect those into S or into sigma, and then actually use this to do some computations. Of course, those computations are not guaranteed to terminate, but we can still run a tactic to do these computations, and if it terminates, we know that you get the right result. So it allows you to extend the IDs from S effect a little bit further than just the decidable ones. And we actually implemented a tactic that does this. I mean, it's very crude, but it does something. There's a so we actually showed that this partial of 1 is a dominance, and that's what you hope, but it's actually true. We've proved it in Coq. And then there's a nice paper by Martin Escardo and a student Knapp that they provide a general construction if you have a dominance. So this is in the theory of synthetic computability inside Hoff. And they have a nice paper about this. And they show that for every dominance you can actually get a corresponding lifting operation. I'm not going to explain what it is in general. But the question they ask is, if you apply this lifting operation with respect to our S, with respect to our Sierpinski space, to X, do we actually get the general partiality model? So that's the question they leave open, also because they mostly work with countable choice, and they say, well, so what happens if you're not using countable choice? And we actually solved this issue. This was mostly a side issue when we were doing the formalization, and this was one of the things that came up. And in fact, you can show that this actually is a classifier for partial maps with open domain. So this is a nice bit of topos theory. So there you would always work with partial map classifiers. And what is nice is that this is actually one of the places where univalence is actually useful, because what you already saw in Egbert's presentation is the notion of the object classifier, and this is just a special case. So this uses univalence in the form of an object classifier. And this again shows that this has the expected properties for the classifier for partial maps.
By that last line, do you just mean that the propositional extensionality holds?
No.
What do you mean exactly?
You actually get, well, the notion of an object classifier, so you can restrict it to any prompt values property. So from the object classifier, the object classifier are the universal properties of the universe. And now if you have some kind of, say, truncatedness property or a modality, then you can the universe of those things are actually, they actually classify maps with those fibers, and this is just a special case of that. So that's, yeah, I think that's a nice use of univalence. It's sort of not expected. There's some what is it, two categorical structure in the definition of a partial map classifier that's usually not name specific, but here it just comes out. Okay, but I mean, this was a bit of a digression to actually show that, I mean, the only thing we were defining is Sierpinski space, and that already gives quite a lot of work, but it's done now. So once we have the Sierpinski space, the nice thing about defining it in this way is that we actually have small, because it's a higher inductive type, so it stays in the lowest universe. And that means that we can define the lower reals. Lower reals are real numbers with the lower topology on it, or their lower cuts in the rationals. And these are very useful in, say, domain theory or constructive mathematics. But usually there would be impredicative, because you would use a power set. But here we actually have small lower reals and small dedicant reals. They have been formalized by Ketan. And once you have the lower reals and the dedicant reals, you can look at the valuations. So valuation would be a map from the opens of A, defined by the Sierpinski space, to the lower reals. So this is very important. Those things would not be continuous, but they would only be lower continuous. And this is an important observation from domain theory, and we also see it here, but that also means that we actually need to define the lower reals here. And then they have a number of properties. So if you apply it to the empty set, you get 0, you have modularity, monotonicity, continuous continuity. And so we know what evaluation is, and this is actually very simple compared to the definition of a measure. And then we have integrals, and we look at only at the positive parts. And so the interesting thing is the integrals actually go to the dedicant reals, because they would be continuous. They would take a continuous function, and the map from a continuous function to its integral is actually continuous, not just lower semi-continuous. So we have a stronger property there, and this is where important insights from topology actually come back to constructive mathematics. And so this is what an integral is. And then you have the Ries theorem, which is a homeomorphism between those two spaces, or just an isomorphism between integrals and valuations. And we gave a constructive proof of this together with theory, in the case that you have a compact Hausdorff space or a compact regular space. And we're actually copying the same proof, but in type theory. To do that, we're going to vary it a little, because we want to define it not only on types that we define to be compact regular, but we want to define it on all types. And there we use a generalization. So Steve Vickers, he looked at our proof, looked at the proofs in domain theory, and he generalized all of this to locales. So then what you want is evaluations, but you also want to have lower integrals. So lower integrals would be maps that are only lower semi-continuous, but in this way you're actually able to integrate more functions. You're not only able to do the continuous functions, but you can also integrate the lower semi-continuous functions. And it's this, and then he showed that for every locale you actually get a correspondence between the valuations on this locale, defined in this way, and the lower integrals in this locale. The interesting thing is that once you have all of this set up in type theory, basically the same proof just works in type theory. And that means you actually have a generalization of this fact to type theory, to a much richer type theory than just locales. So I think that this was a very interesting observation, that this just works. But now that we have this, so the key thing is that once you have this correspondence between valuations and integrals, you get the multiplication of your monad. And that's of course what you want, because you want to model probabilistic computations by using effectful computations, I mean the theory of Moggi. So that's what we have. So we can actually define, well in this case the bind operator, but you This is the formalization monads that Haskell programmers would use, but they're equivalent, of course. So the unit operation is just a direct measure, and this is the way you define the byte operator. So you take an integral here, and you take a function like so, and then you directly write down what the integral here is. So the integral here will take a function and then output a value like this. So this is fairly direct. Now we want to look at what kind of probabilistic languages can we actually interpret once we have this monadic framework. So what was done in ALEA, this Coq library that's the basis for Certicrypt and Easycrypt, is just a standard monadic interpretation. So you have units, lets, you have functions, and you have everything else. So this is a very simple functional language, but it can already be used to do quite a lot. So if you look at what's currently being used in Easycrypt, it's a probabilistic while language, so it's an imperative language. And so you have just the usual imperative while language plus a random assignment. And so you want to have general fixed point in here. I'm going to explain them and how you do those. So this language RML is still fairly simple. So one of the things you want is function types. And this is a big problem. So the function types, that's a big problem with the ordinary formulation of the Giry monad, because say Polish spaces, they're not closed on a function types. So if you want to have the semantics for probabilistic computation, then Polish spaces won't work, measure spaces won't work. You can make it work in domain theory, but that's all very finicky. So the nice thing here is that we're just doing this in type theory. So the H sets that we're working in, I mean, they have all the type constructors, and in particular it's Cartesian closed, so we can just write down these T exponents, and that means that we can actually interpret higher order functions. So we now have a probabilistic language with continuous data types and higher order functions. So this is something that people were looking for. As I said, so here in this while language, we need general fixed points, and we do this because the Kleene category is actually omega CPO enriched. So, and this is because we use subprobability valuations. So the valuations do not need to sum up to 1, but they can have value less than 1. And then, since these valuations are closed under, I mean, if you take a sequence of subprobability valuations, then the supremum is again subprobability valuation. So we can end up with fixed points. So what we end up with is a high order functional language with continuous data types and fixed points. So or recursion. So we get a very rich programming language as requested by Gordon Polkman. So I think that this is already quite nice. But we can go a bit further. So I was presenting this in Paris, and then I met Dan Wang, who was a student, he just finished, of Greg Morrisett. And what they did was they actually came all the way from the other side. They wanted to run their machine learning algorithms very fast on graphical coprocessors. So it's impressive that they came all the way to topological domains because they wanted their semantics to be computable. So they have a compiled, and this is important, so they're actually using programming language techniques for their programming language. Compiled probabilistic programming language geared towards machine learning. And they have high order recursion and continuous data types. And so their language satisfies, I mean, the similar desires as we have. And actually one reason for this is that our semantics is actually basically the same. And this is what we're now working on together to actually show that if you take our semantics in the using the realizability approach, we've done something in the internal language, but of course this can be unfolded just by the realizability interpretation. And then we've already shown that the basic constructions actually are precisely the same constructions as they ended up doing. They ended up doing them by hand, and we just used the internal logic to directly define them. So So this both confirms that what we've been doing is interesting. I mean, it's actually relevant. And what they've been doing are precisely the natural constructions that category theory or constructive logic tells you that are the right constructions. So I think I'm very happy about this collaboration. And one hope is that we could actually use HOP as a verification framework for these kind of things. Then, yeah, there are more people working on getting a semantics for higher order probabilistic programming. And one way of doing this, and this is how you could look at our construction. So you take the observation that, say, topological spaces is not Cartesian closed. So you define a convenient supercategory. So you do sort of your data embedding to get, say you take quasi-topological spaces, and this is a quasi-tuple, so this is something that looks sufficiently much like the type theory that we're using. And you could even do this on certain big tuples, so that there are quite a number of constructions. So this is well understood how to do this, how to make these completions, to turn topological spaces or a subcategory of topological spaces into something that behaves much nicer. So we have such a setting, and then we just add probabilities inside the setting. So this is very similar to what we've been doing. Now there's a couple of recent papers by these people from Oxford and Edinburgh that model high order computation, and they actually go the other way. So what we do is first UNADA complete and then do probabilities. They do the other thing. They take a standard Giry monad, monadic framework for doing probabilistic computation, and then do higher order by just doing a UNADA embedding. And one could hope that, I mean, we're going up and then right, and they're going right and then up. So you hope that this in some way commutes, but I haven't been able to make this precise. But there's certainly a similarity between what they're doing and what we're doing.
Does the Giry monad construction sort of topological space, does it give you, if I feed in, I mean, to go that way and an accent that way, and that depends a bit on the Giry monad sort of behavior.
So certainly you need to negotiate a bit. So I'd imagine that instead, so they're working on measure spaces, but of course you could also start by just doing it on polish spaces, for instance, and then do UNADA. So that would probably be closer in construction. Yeah. So now, I mean, type theory is so nice because it's both a framework for proving, but it also it's a very expressive functional programming language. Now, what we did was we just added axioms to HOT, and so we break this whole functional programming business. So that seems not so nice, but fortunately there's hope for a solution to that. So in our framework, what we've done in Coq, it won't compute. I mean, it might compute by accident if we do a construction that doesn't involve the axiom, or if the reduction just lifts out the axiom. But of course, homotopy type theory has been implemented in cubical and now in cubical ALEA, and the other axioms, the axioms for synthetic topology, have actually been implemented in NUCO. So you could hope to have one implementation that supports both these features. So either in cubical or in something like NUPO. I mean, there's an interpretation of the cubical model in NUPO, so that could be a basis. The people in RedPool are working on making a cubical version of that, so you could certainly hope that that would be a basis for a combination of those two systems. What we've been doing in Aarhus is take cubical and add guarded features to it, and in that process we also make the model more abstract, so you could hope that it helps. There's the work by Andy and Ian on generalizing these models, so you could also hope that that helps to actually get better models of these kind of things. So there's certainly hope in actually getting one type theory that implements all our axioms. So these axioms are motivated by computational considerations. still, even if those actions we've added would compute, we still wouldn't have a guarantee that our programs would terminate, because we're doing general imperative programs. So we have fixed points, so there's no guarantee of termination. But even if you look at ALEA, the ALEA library, they have general fixed points. So already in that case, there's no guarantee for termination. But we still have a semi-decidable relation. So taking a program with randomness from, say, the unit interval, then the semantics would be semantics of this program in this rational interval. And you can wonder whether this interpretation is actually bigger than a rational number. And you can ask that question, and this will be a semi-decidable proposition. So you can state this in your prover system, and then just have a tactic run, and then you can see whether it happens to prove that it actually is bigger than a real number. Sorry, bigger than some rational number. And we've actually tried this, and this works in very trivial cases. But there's certainly hope that you can actually do more with this. Just as in general, you can run non-terminating programs in your type theory by just giving it a number of steps that you can do. So this is more of the general question about doing non-terminating computations in type theory. But it does. So there's hope that our actions can be realized. Even if they're realized, we need to work with general fixed points. But once we've and the solution to that is just effectful computation inside your prover system. Now, if you've been paying attention, then one question is, so how could this possibly work? Because one of the things we can do is to so just the booleans, they're a prime example of a dominance. So if we just interpret all of this with sigma being the booleans, then we're actually requiring all sets to be measurable. And we know that this doesn't hold for the Lebesgue measure on 0, 1. So this actually would contradict the axiom of choice. So how can this work? Well, this is the case because continuously there are actually fewer maps from 0, 1 to sigma. And therefore we can actually hope, or we can actually prove that they're all measurable. So for 0, 1, all the open sets actually have evaluation. So this actually works. But this also shows that the only reason why this can work is because we're deviating from classical logic. And in classical logic it doesn't work because of the counterexamples based on, that contradict the paradoxes of measure theory in classical set theory. So here's actually, this is I think a strong point of using constructive logic to reason about probabilities. So this is what I've tried to show you. So we do probabilistic computation with continuous data types, so that's the important point for you. We can now also do continuous data types and have an axiomatic semantics for programming languages like in ALEA. We use HOT to replace the use of setoids, so this gives a real simplification of the library. It's an experiment with synthetic topology in HOT, and this is nice because it's a way of developing predictive constructive mathematics without choice. This hasn't been done yet. There are a few experiments in the HOT book, but this drives it a bit further. A Giry monad, an extension of the Giry monad from locales to actually synthetic topology, and it works very nicely in that setting. We model higher order probabilistic computation inside the H sets, inside homotopy type theory, and this may look like a curiosity, but it turns out that the constructions we did are actually the constructions of a very fast programming language made for machine learning, and quite a bit of our work, some 6,000 lines of code, have actually been written in Coq for a library for this based on HOT and math classes. So that's what I wanted to show you. Thank you.
So I have a number of related comments.
So first of all, it seems that what you're actually using takes place inside the H sets, right?
Yes.
So you could, for the semantical purposes, you could just do a variation of the groupoid model in whatever setting that you're working on.
No, we could also take just the realizability stuff, so maybe the realizability semantics. The problem is that we want to, well, the point is we want to use the proof system, and a nice way of doing a semantics for type theory would be, or is, go to higher levels. But I agree, yes.
Okay, but that leads to the other question is, so if you wanted to use something with higher dimensional types, as in you have available in pod, it seems that maybe you should incorporate some ideas from Mike Schulman's real cohesive hardware. You would, because what you're doing only really works for H sets, but if you wanted to have the synthetic topology on high dimensional types, you can do that via this real cohesion. And that also would allow you to phrase a version. You could use classical logic on the crisp types, as he does.
Yes.
You could have the crisp law of excluded middle, and that would not contradict the continuity principles that you need.
But it's using algebraic topology instead of synthetic.
It's a combination, right?
Well, it's a combination, but it's. I don't think the connection between algebraic topology and measure theory has been very well worked out.
Well, it's only if you really needed to do measures on continuous groupoids or something like that.
Yeah, but we don't do this yet. Okay. Thanks. Andrea?
I had a question. Where does the guarded feature, where's the guarded feature needed?
Oh, it's not needed. I was just stating how we could, so we've added axioms to HOT. So this would break computation. And now I'm speculating or pointing out directions on how to actually make models and implementations of this. So what I would hope is that we could actually take the ideas from the way the axioms for realizability have been embedded into NuCode and make a model based on this, like the way we made the guarded cubicle model, and then implement this in Agda, for instance. So I think that would be.
What were the axioms that you added? Because I mean, the sigma you constructed as a hit, right?
Yes.
What else?
So this one, the weakly sequential open, and also the defense theorem. So you need.
Oh, I see. You're just postulating that those
Yes.
are true. So, sorry, had you finished your question? So if I wanted a concrete model of all that, where do I look? Do I look in the univolar model in simplicial sets and hope for the best? Is that the...
Well, that's what I said. So,
So
you take any of those, but neither of those completely works yet.
Okay. So what doesn't quite work yet exactly?
Well, the cubicle assemblies is an idea that has been around for quite a while, and there's progress on that.
But if you just say simplicial sheaves, right? So what's
so simplicial sheaves
what's
work,
lacking?
but there they have weak universes, and people like to have strong universes. Although even for Coq, it's not entirely clear that it uses strong universes.
But it uses something way stronger than anything you can get from simplicial sheaves.
So this is certainly would give a model of our axioms, and it would, but the universes would be slightly different. As I mean, most remarked, most of the constructions work on the sublevel in any case. But this is just a way to actually use the hot library to do these kind of things. Also, so it's just so what theory has is cubicle stacks over Cantor space, and that should actually give a model of our actions. What hasn't been checked is that you actually get the Venn theorem on the level of H sets, and that should work, but the details haven't been checked. So I think that this would be the best bet. The thing is that this would satisfy the axioms, but it's still not, it doesn't give the realizability model that we're actually interested in. Because, well, realizability model is also what's been implemented in this probabilistic programming language for machine learning. Let's close the brackets. Andreas, you were happy. Jeremy had a question first.
No, so what is it that you actually take from Pod? Is the quotient types, function extensionality,
Yes.
and the construction of sigma?
The construction of sigma, and then we add these axioms. And yeah, there's a small excursion about the partial map classifier, which uses a bit of univalence. And of course, to prove things about the higher inductive types, you also want to have univalence.
So one question is, so when you want to compute
Yes.
the monads, this looks to be a very conductive approach to have like you could try to prove something like productivity and get more and more information.
You mean with partiality?
Yeah.
Yeah.
So this is, but that's a usual, yeah, okay.
Yes.
But when I ask
Yes, the observation is just that before, so we don't formally know yet that how to get a good co-inductive definition of this. And I think it's indeed right. If you use the co-inductive types in cubical, then it would actually work.
Okay. And the other question is just like, so I mean, most people who work in probability theory want at some point to have something like the back measure or the evaluation. How much work do you think it would be to have it in the setting?
That wouldn't be too difficult because you just, well, basically you just say what it does on the rational intervals.
Okay, that's enough.
Yeah.
And then you have all the lifting already available too.
Yeah, I mean you need so you need the Venn theorem to have the finite coverings, and then there's a bit of combinatorics involved, but not too much. So you only need to define the measure on open sets, and well, that's not too difficult.
And how difficult is stuff like product spaces, like or infinite sequences of random values?
So one of the things Steve Vickers proves is that actually the monad is commutative, and that's basically the Fubini theorem. And I think that's 2 or 3 pages. Yeah, that shouldn't be too. Yeah, that would certainly be nice to formalize it. Yeah, but that's a short argument, and it's a lot of it goes by universal properties. So that should be and free constructions. So that's precisely something that things like higher inductive types actually work very well.
Just wanted to understand this remark about the semi-decidability if you wanted to check determination. Is this different than just running the program and see if it falls, or is there some sort
No,
of...
it's just running the program. See if it falls.
Okay, okay.
and you can do you can do some heuristics, of course.
Yeah, because the totality of, I mean, given an argument for all arguments it falls, that would not be semi-decidable.
No.
But could you state that internally and then prove it?
Prove that it's semi-decidable.
No, prove termination over all arguments or all inputs. Can you state and prove that internally in your setup? You have some